Today we're going to talk about the properties of logarithms. So we're going to take the rules from 3.2 and we are going to apply more information to them. We're going to talk about the properties and we're going to talk about something called the change of base formula, which will allow us to utilize a calculator on some of these where before we couldn't have. So that's what we're going to look at for 3.3. We're going to talk about three properties. And these properties come from the power rules that occur when we're dealing with any type of multiplication with exponents. So first let's look at the product property. Basically, if we have inside of a logarithm, base b, a multiplication, a product. Think about the rules of exponents. The rules of exponents say that we can add up the exponents if those things matched. Well, what's interesting about logarithms, we can actually split up a multiplication into two separate logarithms as long as they add together. So if you have a multiplication inside, we can split it apart into two separate logarithms and add them. And this all comes from the rules of exponents, that if the bases are alike and you're multiplying, you add the exponents. That's kind of basically where it comes from. Next is our quotient property. If inside of a logarithm we have a division or a quotient, so you could probably write that as x over y. That wasn't easy to type, so if you put x over y. Basically, because of our rules of exponents being that if the bases are alike and we're dividing, we subtract the exponents. What happens here is we can split it apart into two separate logarithms if we subtract. And it's always the log of the top minus the log of the bottom. So that's the quotient property. Now, the power property basically comes from the fact that if we have a power to a power, we distribute that power that's on the outside to the things on the inside. So that's where our power property comes from. So basically it says that if we have a power on something on the inside, we can actually take that power and drop it down in front of the logarithm that it is on. So if we have a power on the inside, we can take it off and put it in front of the logarithm of the thing inside. So let's look at how we would use these properties to help us. So let's start with the first one here. Express the log of 96 in terms of 2's and 3's. So what they basically want us to do is break apart the number 96. So start taking the number 96, and you might recall back from an early math class in your life, the factor trees, and you can start breaking it apart. And we're looking at for 2's and 3's. Sorry to bother, but do you have then we would keep breaking it down and breaking it down until we see 2's and 3's. So I'm really now, bless you. I'm just breaking it down into taking out as many 2's as I possibly can. So what I found was that 96 is the same as 2 to the 5th times 3 to the 1st. So I broke it down as many prime numbers, 2's and 3's, that I could possibly break it down at. Now, we are going to use our product property. Our product property says that if we have inside of a logarithm two things that are multiplied together, that we can split them apart. And it is the log of the first thing plus the log of the second thing. Now we almost have it the way that they want it. They wanted it in the terms of log base or the log of 2 and the log of 3. The only thing that is messing that up is the 5. But the product property says, or I'm sorry, the power property says that I can drop that 5 down in front. So it's basically going to be 5 log of 2's plus the log of 3's. So that is the answer that you want right here. Because we have taken the expression, the log of 96, and rewrote it using only logs of 2's and logs of 3's. Now let's do the same thing for part B. So we want to really break apart 32 over 9. Well, if you do the factor tree, or if you just know your factors of 2's and 3's, 32 is the same as 2 to the 5th. 9 is the same as 3 squared. So when we see this fraction, we want to immediately rewrite it as 2 to the 5th over 3 squared. Now it's a quotient, it's a division. So the rules of logarithms say that I can break it apart into 2 separate logarithms if I take the log of the top minus the log of the bottom. So now I'm going to rewrite it as the log of the top minus the log of the bottom. Now the only thing that's wrong with this now is that our powers are inside. We don't want up 2 to the 5th inside of our log. We only want 2's to show up inside of our log. We only want 3's to show up inside of our logs. So to take and to fix that, we're just going to drop those powers down in front. And so then our final answer becomes 5 log of 2 minus 2 log of 3. And that is our final answer. Let's look at example 2. So we're going to use some of those same rules to help us simplify things in a slightly different way than we did before. Before we were always asking ourselves, okay, what power would do that? Well, now we still can ask that question, but now we can manipulate the algebra to make it a little easier for us. So the first thing you always want to look at is what's our base. So for example 2a, our base is a 2. So let's take the number 32 and let's rewrite the number 32 as a power of 2. Now you might recall 32 showed up on the last example. 32 is the same as 2 to the 5th. Now you might also recall a rule from Algebra 1 that says if we have a something with a power inside a radical, we could rewrite that as the top is the power and the bottom is the index of the radical. So let's take that same rule and let's apply it to our number here. And so that is the same as 2 to the 5/3 power. Now we're going to set that inside of our radical. So instead of rewriting it as log base 2 of the cubed root of 32, let's write that as the log base 2 of 2 to the 5/3. Now what's really cool about this, there's lots of things you can think about at this point, but this 5/3 can technically drop down in front. So let's drop it down in front. So we get 5/3 the log base 2 of 2. Now we know that this sorry about that. Let me fix that. So we can drop that 5/3 down. We know that this is the same as 1. Because what power do you put on a 2 to leave it a 2? We know that cancels, and that's a 1. So the answer is just 5/3 times 1, or 5/3. But you could have even seen that at this phase right here, because what power do you put on a 2 to make it 2 to the 5/3? 5/3. But you can see how the power rule also works. So we can drop it down in front, then cancel it. Okay. Let's take a look at part B. For part B, I like the fact that these two things match. Because those two things match, it's going to make our life a little easier. Now first, let's use our power rule. Let's take our power and let's drop it down in the front. Okay, let's take our power and let's drop it down in front. If there is something already out in front, it is going to multiply by that thing. So this is 3 times 4, natural log of e. This is 2 times 2, natural log of e. Now remember that the natural log of e is equal to 1. So this is 1, and that is 1. So this is 12 times 1, and this is negative 4 times 1, which is 12 minus 4, or our answer is 8. So by using some of our rules, we can cancel things out rather quickly. We can make them numbers rather than logarithms. So anytime that is something that you think is going to work, use it to your advantage. Now let's look at example 3. Now sometimes the instructions will tell us to expand. That means they want to take where you're only showing one logarithm, and they want you to pull it apart into as many logarithms as you possibly can. Okay? So you might notice that inside of our logarithm, we've got a multiplication. That means the product rule. That means that everything that is multiplied inside, each factor inside of that multiplication, can get its own logarithm. So this can rewrite as the natural log of 4 plus the natural log of m cubed plus the natural log of n to the 5th. Now to expand it properly, you don't want to leave any powers on your things that are inside. So to expand it, we want to expand it to the point where all powers have been dropped down. So the last step here is to take that front power and drop it down in front. And so then our final answer, this thing is expanded as fully as it can if we write it as natural log of 4 plus 3 natural log of m plus 5 natural log of n. And that's really pretty much it. Now don't mistake factors for sums or differences. We can only split apart things that are multiplied or divided. We can't split apart any pluses or minuses that are inside of there. So we're talking about factors. Okay. Speaking of which, now we go to the bottom. Okay. The top is in factored form. That's as far as you can go. You can't do anything with a 2x minus 3. So I would put that in parentheses. Let's take a look at the bottom for a minute. I'm going to rewrite that as 3x to the 1/4. So you want to take any radicals that are there and you want to rewrite them using fractional exponents. Now, I'm going to use the quotient rule, which says that I can split apart a quotient or a fraction by taking the log of the top minus the log of the bottom. Let's do that. So it is the log of the top minus the log of the bottom. Now you might notice that this is not something that can factor further. So that is the one factor. It's done. But this one does have two distinct pieces multiplied together. That is two distinct factors. So we can split it apart. Now be careful when you split it apart. You have to account for the fact there's a minus there. So you would be minusing all factors that are in that particular thing. So you would get the log of that first piece, no changes, minus the log of the 3, minus the log of the other term. So that minus distributes to both pieces. And you got to think about both of those things were in a denominator. Both of those things were a division. That's why they both get a minus. And what do negative exponents indicate? Negative exponents indicate division. They indicate that something was in the bottom, so that's why they become negatives. Now, the only thing left, or if any powers are showing up, we have to take a second and we have to drop that power down in front. Then we know we've expanded as far as we possibly can. So we get the log of 2x minus 3 minus the log of 3 minus 1/4 the log of x. And that is expanded as far as we possibly can go. So now let's go the opposite direction. So now let's take and go backwards. Well, to go backwards, remember, on the last problems, the last step that we did was to drop the powers. So the first step we're going to do is we're going to bring the powers back inside. So the first thing we're going to do, you look for any numbers in front of your logarithm that are multiplied by your logarithm, and you're going to bring it on the inside as a power again. So we're going to rewrite this as log base 4 of x to the 1/2 minus log base 4 of x minus 2 squared. Then you want to note the signs. Anything that is a plus between them, indicates a multiplication. Anything that is a minus between them indicates a division. So we want to think about all the positive stuff be on the top of our fraction and all the negative stuff to be on the bottom of our fraction. And that's a 3 power there. So our first piece is positive. It's going to go on top. Our last piece is negative. It's going to go on the bottom of our fraction to put it back together. So we get the log base 4 of the top thing, x to the 1/2, over the bottom thing, x minus 2 to the 3rd. And now we have condensed it as far as it possibly can go. Now, you might want to make the x to the 1/2 a square root of x, but it's fine leaving it just like this. So for expanding, you're using as many logs as possible. For condensing, your goal is to try to get it down into one single logarithm. Let's go one more. So part B, we're taking the 5 and the 6 and bringing them back inside as powers. So we get the natural log of x plus 1 to the 5th plus the natural log of x to the 6th. Now note the sign between them is a plus. That means we can bring them inside of a one logarithm if we multiply them. So we get the natural log of x plus 1 to the 5th times x to the 6th. And you can even put like a bracket around to indicate that that's the whole thing inside of that logarithm. So that's how you condense them. Now this is our change of base formula. It's going to allow us to use a calculator for things that we didn't necessarily use a calculator for before. Now, let's say that you have the log base b of x, and you can't clearly see how x is related to b. You can't figure out how to change x so that it matches b. So you're kind of stuck. Well, what you can use is the change of base formula. And it says that the log base a of x over the log base a of b is the same as the log base b of x. Now, on a calculator, we're stuck with log-base tens and natural logs. So I like to think about this as the natural log of x divided by the natural log of b. If you like the log button on your calculator, the common log, you could also go the log of x over the log of b. As long as you use the same button each time, it's going to work. So like if we have the log base 5 of 72. Well, I normally would say, I have no idea. You know, I can't make the number 72 to show up as a power of 5. I could probably guesstimate and get close to it, but getting exactly to it would be very difficult. Well, instead, what I can do is I can use a calculator. I can do the natural log of 72 divided by the natural log of 5. And I could get a real close approximation. It will be decimal values most of the time, but like this is approximately, and go like 2 decimal places out if you're using a calculator, unless the instructions tell you differently. That would be like around 2.66. And that's not something that you would clearly get on your own. So this change of base formula is really nice. If it's numbers that you're a little unsure about, you can always check it with a calculator. Now let's go ahead and look at some examples using the change of base formula. So that first one says the log base 6 of 4. Well, think of powers of 6. You know, 6 to the 0 is 1, 6 to the first is 6, 6 to the second is 36. 4 doesn't ever show up in there. So what we can do is when they don't match up really, we can do the natural log of the inside over the natural log of the base. And we can put it into a calculator. Now, these are going to give you usually very strange decimal values. And again, just take and round it to like 2 places. So let's go, it's approximately 0.77. Now, the way that you could check this is we could take 6 to a power of 0.77. Remember, the answer to a logarithm is the power that works that way. So 6 to a power of 0.77 will be really super close to 4. So that's the way that you could check it. Let's think part B. There's no way that you can flip around a 1/3 or use powers on a 1/3 to turn it into the number 8. It just doesn't work. So we can use the change of base formula. This time let's use the log button instead of the natural log button. They both will work just fine. It's kind of your decision. And so that would be the log of 8 divided by the log of 1/3. Like if you put them either in the calculator and the one person hits the natural log button and the person next to them hits the log button, you'll get the exact same answer. Okay? So if you do the log of 8 divided by the log of 1/3, you get an answer of negative 1.89. Now let's talk about why the answer became negative. Negative powers flip something. So the only way that you could get 1/3 to start acting like an 8 is if you use a negative power to flip it over to up. Think about a negative 2. 1/3 to a negative 2 flips it and squares it. That's 9. So wouldn't you expect your answer should be a little less than 9? Or I mean a little less than 2 so that you could get a number a little less than 9? So that's why it works the way that it does. And that's what the negative indicates, is that you were kind of using reciprocals to get where you needed to go. So if you get a negative answer, the powers can be negative. It's just what you plug inside that can't be negative for a logarithm. One through 7 and 9 through 15 are like my first example when I was breaking it apart to be 2s and 3s. Just follow their instructions. Like 1 through 7, you're using 2s and 5s. 9 through 15, you're using 3s and 7s. So you want to just take that number and start breaking it down. For number 19 through 27, that was like, I think it was maybe example 2 or 3. Those ones you're just using your rules of exponents to simplify that as much as you can without a calculator. Number 29 through 35, you're expanding as far as you can, using as many logs as you can. Number 39 and 40, you are going to condense them back down into one logarithm. For 49 and 50, you're going to have to use a calculator. For 69, it's an expansion one. It's kind of a little harder. I wanted you to see a more difficult one. 61 and 62, you're going to have to use a calculator again. And 76 is condensing back inside of one logarithm. Okay? So that's your assignment. So you can go ahead and try those.